the great presentation earlier. But yeah, this is kind of round 2 of a talk that Max and I almost gave 2 years ago at the previous protocol Berg. I ended up breaking my ankle just before the talk, so didn't make it. Max had some screen issues, so a lot of things kind of like didn't quite work out. But we're very happy to be back with a kind of update on the work that we've done in the meantime. So this talk is going to focus on Nym for Libp2p. And what we did back 2 years ago was work with the nice crew at ChainSafe on a proof of concept for Nym and Libp2p for the Ethereum Lighthouse consensus client. 2 years have passed. We were very busy building a VPN in the meantime, the Nym VPN, which we're also very keen for everybody to try out. But we are now back on the work with integrating Nym into Libp2p, and this time with a different use case, namely for Celestia and the data availability layer. So this is what we're working on at the moment. We're going to do kind of a little bit of a kind of conceptual thing in the beginning, and then we're gonna, hopefully get kind of a little bit more hands-on for those of you who want to get involved, because this is, after all, a workshop rather than a full-blown talk. Yeah, so what we kind of would like to start off with, yeah, so this is the overview. Here are some download links. I'll share this again a little bit later. But for those of you who are kind of keen to get started, feel free to jump right in. But to start off with a kind of conceptual background, and this was like a piece that I'd fleshed out a couple years ago in a little bit more detail. This year, I'm going to keep it a bit short because I would like for us to get to the practical stuff. Also, I'm giving a talk at 4 p.m. This afternoon that's going to go a little bit more into the kind of philosophical aspects. But a bit of background on kind of, Nym. So Nym is, we build privacy software at Nym. There's been a lot of kind of like work on the topic of privacy, both on the technical side, but also on the kind of mimetic and narrative side. And there's, what we're noticing is that privacy is still kind of backed into this mimetic corner. It's still very much kind of this thing where whenever you try and get people to use privacy software, you almost have to like threaten them into using it and say how big and bad, all the kind of potential baddies out there are, and therefore you need to protect your privacy and you need to use all this very complicated software. And we're kind of hoping to kind of start moving out of that space a little bit. So, conceptually, let's say there's this, idea of like, okay, so either you kind of, when people think about privacy or think about surveillance, they think kind of, you're either in like total surveillance and there's this, kind of desert metaphor, or there's complete privacy, which is this kind of threatening void almost of information or lack of information. And there's also this aspect of privacy mimetics that tends to kind of retreat back into the individual and the individual protecting themselves and the individual as a kind of like unit. So we want to like loosen up a little bit these categories and work more with this idea of the forest as a metaphor for privacy. And, the reason why the forest is interesting is because it's not so much of a kind of either or. When you walk through a forest, you get this kind of these dapples of sunlight, there's some shade, there's various grades of shade. And also it kind of opens up for this idea of like privacy as actually as a design space. There's been people that have kind of worked on this a little bit before. So our friends at DarkFi have worked, a lot on mimetics, and this idea that, privacy is not just kind of, or the dark is not just the absence of light, it has its own qualities. I think what we're trying to kind of do is expand even beyond this idea of privacy equating the dark, and positioning privacy not so much as a threat, but as an attractive design space. And kind of to think this through a little bit more in practical terms, cryptography is, very widespread across the world. It just, doesn't have necessarily always such good marketing, let's say. But there is, this design space is an important space. It's literally the locks, the windows, the doors, the building blocks of the digital space in quite important ways. So, a little bit of a kind of beginning of mapping out privacy primitives. It would be great to get a little bit of input on that. One of the privacy primitives that we're going to be focusing on in this talk is the concept of unlinkability, which might not be as familiar as the other ones that are listed here. That is what the Nym mixnet really offers in the Libp2p context. So we're going to go into that in a little bit more detail. I also listed Web3 privacy now here. I don't think Mikkel is in the audience right now, but I think they have done some work on mapping out the privacy primitives as well. And I think kind of that as a shared, let's say, a shared piece that's like done across, those of us, in this space that are working on privacy technology is quite important to start to showcase this really as a design space. Yeah, so I think I might leave it there. So in short, what we're going to do here is really focus on Nym in the case study of Nym in Libp2p for Celestia specifically, and also what unlinkability is, and more specifically, what unlinkability the challenges that unlinkability poses in a P2P context, because it kind of creates some, interesting dynamics. Yep.
Okay, so now to the technical side, we're going to, I'll do a brief overview of Libp2p for everyone that's here, so everyone's on the same page. Then go over Nym, and then we can look at how smashing those two things together brings out some interesting stuff. So Libp2p itself, basically, modular set of protocols, specs, libraries that easily enable people to develop peer-to-peer network stuff. So it sprung out of IPFS. It was originally their networking stack that they then abstracted out because there's no reason for everyone to recreate and maintain their own networking stack, right? You might just want to do something like build Filecoin or the Lighthouse client or run Celestia on it, Mina, Substrate. There's loads of stuff that uses Libp2p, right? And basically, it's just a set of standardized interfaces, addressing schemes, gets rid of all of the gnarly development stuff that maybe you as an app developer don't really want to do. And there's a really good essay on the Zcash blog, actually, that kind of goes into the reality of inheriting someone else's networking stack. So Zcash originally just forked Bitcoin, and because of that, then had to go with the design decisions that were built into Bitcoin that then were increasingly no longer advantageous for Zcash to have. And, they go into it in this piece where I think at one point they ended up with their connection logic was a hundreds of lines long C++, struct. And it was just very increasingly difficult to maintain and pick apart, right? So what is Nym and why does it exist? It's a decentralized, incentivized mixnet. So you will be these three attributes on the side here, right? We have the top one and the bottom one formed together to create the anonymity feature that comes from it, right? So it's an overlay network. Basically, traffic is routed through multiple nodes. So no one on no particular node ever has a full path of or a full picture of where anything's going, right? So this is your I think everyone here will probably be familiar with this. This is a similar thing to what Tor does, right? You're just unlinking your origin and your destination, or your sender and your receiver, from any observer who is running part of that network, right? The two aspects that the mixnet adds on top of this, so the anonymity basically is you add timing obfuscation. So basically you reorder packets as they move through the mixnet at each hop. The mixnet also involves 5 hops instead of 3. And traffic moves through the mixnet, unlike Tor, where you basically just set up a circuit. So you start streaming all of your traffic through those 3 nodes. With the mixnet, we actually break everything down into packets, and I will go into that a bit later. So this is where your timing obfuscation comes in, which is preventing your traffic analysis, attacks, and stuff like this. And then on top of this, or into this, essentially, we have this concept we're talking about, the noise generating mixnet, right? So noise in the form of covered traffic. So traffic that looks is encrypted and is the same size as Sphinx packet as normal traffic that you're constantly sending into the network and that you're slotting your real packets into, right? So it's creating this constant level, essentially, of entropy in the system, which makes it, for an observer, very difficult to then pick apart. So this is like a very high level flow of basically you have a client on one side, you're having a client on the other. For the purposes of this talk, let's imagine that both of these are peers in the Libp2p network. Maybe they want to do gossip sub or something. Cover traffic with real packets kind of mixed into it, all encrypted in the same format, which is the Sphinx format, and they're all the same size, so they're all padded. Leave your computer at a constant rate, which is defined by a Poisson process. And then basically your traffic will go through 5 hops into an entry gateway. It will then go through 3 mix nodes. And the mix nodes is where you, as the name kind of suggests, right, you get the mixing happening, which is basically, imagine it kind of like every time you pass a message, every time you pass a packet to a mix node, imagine you kind of like hold that for a variable length amount of time. You shuffle those packets like a deck of cards and you send them out in a different order than you got them. And then it goes from an exit gateway and to another client. So that's like a super high overview. We're now going to dig into the, sorry, I skipped forward on my own slides. So, right, if I want to send a message from client to client, I will basically write my message into the payload of a couple of Sphinx packets and kind of send them through this flow, right? Now, each packet is actually routed on its own as well. So this is another key distinction from Tor, right? With Tor, you set up a circuit and you're just streaming through that. But all of our packets are actually routed independently as well and then reassembled on the other side. Now, that's great for privacy, right? Like that's great for, okay, I really want to send whatever the message of your like packet payloads is. I want to make sure that that is hopefully impossible for someone to like tell that like these two clients are communicating with each other, right? But, and this is kind of like the main focus really on the tension between having unlinkability as like a privacy attribute in a peer-to-peer system will come in later, because even though that's absolutely great for privately sending messages between two peers, it's kind of very weird for upstream applications, or it is unusual for kind of upstream apps, right, that are kind of just using the Nym network as a transport layer, right, just sending it through this client instead of, for instance, using like an HTTP client. And you're expecting stuff like handshaking and streams, and you know the mixnet is kind of, it's kind of like a very slow UDP. So you don't get like message ordering. You have to do all of this stuff on the other end. Differs in that you do have guaranteed message delivery. So yeah, basically, let's dig into kind of how this works on a like a nitty gritty level, and then some of the quirks that come out of this. So if we look at this first hop now, right, which is also, by the way, if anyone, because it's like quite a cozy setting, if anyone has questions, just like put your hand up and we can go through it like as and when. Just, yeah, stick your hand up and shout if you have any questions. So this first hop, right? So what actually happens when like I, as the client, I have an app that is going to use Nym, and I actually want to send a message to someone else, right? So this is, I'm really glad it's a really big screen. So on the left-hand side, you've got your local machine, right? And this is like very generic. This is partially kind of like, this is a little bit of a modification of what I have in our docs, but like the QR code was up there before, or it's just nym.com/docs. So this thing on the left-hand side, which your local machine, right? You can imagine the application logic here is like something that is running an app that's using gossip sub, and it's using like the Nym transport to actually like communicate between pairs, right? So there's two things that are constantly happening whenever you have a Nym client that's connected to the network, right? At the top, you have this, actually, let's go through it in order, shall we? So originally, what you do is you create this like a long-lasting relationship with a gateway that you use as your like first hop into the network, right? The entry gateway. And this actually partially defines your Nym address itself, because the network is, the network kind of handles routing for you, which will also come up later because it's a bit weird compared to what most Libp2p things expect. But you basically like, so you just do, excuse me, Diffie-Hellman, create a WebSocket connection to this gateway, right? And then you're doing two things. You have two streams of traffic that are consistently being sent whenever your client is online, right? Between the client and the gateway that it's talking to. And one of them is like just sending cover traffic. So you're basically just sending like empty Sphinx packets at a consistent rate, right? So from the perspective of an observer, if we kind of kick back here, right? These, like this cover traffic that's going here will be moving at a consistent rate. So you can't necessarily try and detect any like bursts of traffic, which then immediately kind of reduces the ability of traffic analysis to go, oh, okay, well that client is obviously talking to someone at this point, right? You're kind of removing that that metadata from any kind of analysis that can happen, right? And one of these streams, that's all it does. It just continuously sends cover traffic, which is not very interesting for actually using it, which is where we get to the second one. So this is where, you know, your application, I don't know, you send a subscribe message to a particular gossip sub topic, completely lost the word there. And what actually happens then is your application logic will then essentially put this in a queue, and the queue will, your client will constantly be checking, right? Okay, oh, suddenly there's something in this queue for me to send. There's some bytes for me to packetize right to the payload of a Sphinx packet and send through the mixnet. And what will happen, as is kind of demonstrated here, is that these kind of like real packets will be slotted in at exactly the same rate. So basically, you're just kind of like consistently sending cover traffic on a heartbeat. And as soon as you have real packets to send or real data to write to a payload of the Sphinx packets, because they're the same thing, then you just kind of slot those in there, right? So just imagine this like consistent queue at a consistent rate of packets that from the outside look exactly the same, right? So now we get to the kind of mixing part of all of this. This is kind of as it travels through the mixnet infrastructure itself, and you get the mixing aspects there, which prevent you from kind of like following streams of traffic, and you get the timing obfuscation, which because most surveillance techniques really are like relying upon probabilistic de-anonymization, as soon as you start adding in like variable delays and timing obfuscation, then it becomes, even if you can go, oh, okay, well, we think those two clients might be talking to each other within this period of time, following the packets themselves actually becomes like impossible. So what does this look like? Sorry, I hope everyone's likes mermaid flow diagrams, because there's quite a lot of them in here. So yeah, basically, right? That's the entry gateway. Okay, the client has sent it a bunch of packets. What does it do? It gets some Sphinx packets in. It does two things. It will decrypt the outer layer of the Sphinx packet, right? So you can think of the way that we encrypt everything. We multiply encrypt everything according to its root. So similar to onion encryption, right? Goes to a hop, peel off the outside layer, because that node can decrypt it. Does a bit of checks some message authentication codes just to double check that like, okay, this isn't like a spam packet that someone's been kind of like throwing into the network. And then your gateway will not have this timing delay, right? So that it will just immediately kind of first in, first out, decrypt the outside layer, go, oh, okay, this needs to go there, check that the MAC is valid, and send it on. So mixed nodes basically do the same thing, apart from the fact that they actually hold those packets for like a variable amount of time. So you're breaking the first in, first out kind of traffic flow that would allow you to, even if you were like, okay, I think I can guess that that packet is there and that packet is going somewhere and I can follow it and try and tell, this then becomes impossible, right? And this happens between mixed node layer 1, layer 2, and layer 3. The layers themselves in the mixnet are not particularly important here. Like, basically, we have like a stratified topology, and what that basically means is that like once an hour, where you are, so like which hop you are in the mixnet, if you're running a mixed node, will change. And the reason we do this is basically to make it a lot more difficult for anyone who's just gonna then try and like, not quite Sybil attack, but just like spam the network with like, okay, cool, I'm gonna set up like 400 mixed nodes, and I will try and make like a single path through it, right? And we have a bunch of other stuff in terms of stopping kind of Sybil attacks with like a reputation system, but that's maybe going a bit too far off the track for this. Yeah. Okay. Just to repeat that for the recording as well, had a question about throughput and latency too. So, yeah, latency is something that is something that you have to take, you have to be aware of for your like upstream apps as well. And this is actually like one of the points later on that I have. But basically, like, you know, just looking at a ping example, for instance. So like the Libp2p, like, you know, ping protocol, just a little heartbeat to check that a client's there. Sometimes you are looking at a ping of like a second and a half, 2 seconds, right? So you are adding like quite a considerable amount of latency to it. And yeah, this Poisson process, this kind of, which you can basically think of as like the defined rate that both of these streams are being sent at, because that is defined, then it's this, there's a balancing act to be made there between, do you send loads and loads and loads of empty packets and then be basically like computationally that's more expensive because you're still like root encrypting these packets, right? And in the case of the VPN product, which is built on top of the network, you're paying for them. So you would like drain your bandwidth quite quickly versus having a higher throughput itself. At the moment, the throughput is definitely good enough for like, let's say peer-to-peer gossip sub and stuff. One of the ways that it starts to, one of the places that like it starts to get a little bit heavy in terms of like back pressure is maybe if you're trying to sync a light node or something like this, right? So we did some work with Zcash, which is like you're then, because you have to set up like multiple kind of streams, you either have to run loads of Nym clients or stuff just becomes like quite a lot slower. This is something that we're currently working on in, or like looking at in R&D of like maybe kind of increasing the size of blocks or using something like this to kind of to get past. But yeah, like at the moment your throughput is somewhat restrained. The number will come, the actual number will come back to me later in the talk and I'll remember it. Cool, okay. Yeah, okay, great. So final hop. So all of your packets, they've gone through this process of being decrypted, checked, held for a variable length amount of time, passed to another mix node, and then all of your packets have to essentially re-aggregate because this is by packet, right? So like if you send 10 packets with the payload inside it, they will go through different mix nodes, each one of them, right? So they all have to then be re-aggregated at the exit gateway. So the exit gateway, it gets all of these packets, it unwraps another layer, and it goes, okay, great. I can actually finally now deliver this to the client whose app can then do something with this traffic that has kind of been sent to it. And this is basically like the same thing has happened with the with your connection to your entry gateway, but in reverse. So I don't think we need to like go too deep into it. But now we get back to unlinkability, but also usability, right? Because it's like, well, how do you reply? How do you reply without doxing the person, like doxing yourself? Because most of the time, you are going to want to actually be sending a message to someone so they can do something with it and get back to you, right? And this is where our anonymous reply scheme comes in. So we basically have the anonymous reply system that we use, which is kind of the key for unlinkability over time, right? Because the concept of linkability between two peers is predicated on the fact that you communicate with each other more than once, right? It's this idea that like, oh, okay, cool. Well, if I'm like always sending, if we imagine that this is like, I don't know, like an HTTP server or something, right? And it's like, well, if the same person is always sending a request to that server at like, I don't know, 9 o'clock in the morning, then even if you don't know what the actual contents of, even if you don't know what the contents of the payload are, or you don't know where it's coming from, you still start to build up like some pattern where you're like, oh, okay, cool. There is someone who is like starting to do this at a particular time every day. Maybe they live in a time zone where like, that's when you kind of wake up and turn your computer on. Like all of these kind of like small, which sounds really inconsequential, but when you start combining those like bits of data that are like aggregated in these enormous data sets, they can actually become like quite powerful tools of de-anonymization. So I've just we've gone through this whole dance. There is a message, there is a payload that's got to this client. It's worked out what to do with it, and it now wants to send a reply. We use SERBs, which are single-use reply blocks, and what these basically are is the client, the sending client, will essentially send like a pre-addressed set of letters back to itself, right? Along with those messages that it's sending out. And the receiver of that request, so our client on the right-hand side, then basically has this pre-addressed set of letters that it can't see the address of, but it can write to the payload to. And because the headers, so the routing information, is pre-computed, then the receiver never actually knows the address that it's like writing a response to, right? Because we have this kind of multiple encrypt, because we have everything multiply encrypted, all it can see is the first hop back into the mixnet from its perspective, which is its own gateway. So nothing is being leaked there in terms of actually being able to reply like properly to people. The flow of this again is, so your sender, the one on the left-hand side, with its messages, it will create a bunch of like pre-computed Sphinx packet headers, and it will send those along with the messages that it's wanting to send anyway, right? So the HTTP request payload, it'll come with all of these pre-computed headers, these pre-addressed letters kind of along with it. It'll travel through the mixnet, and in this situation that's kind of outlined here, then maybe your client on the right-hand side actually goes, oh, well, I wanted to write, 200 bytes of data, but I only have enough Sphinx packets to write 150 bytes of data. What do I do now? And what actually happens then is you then use one of these pre-computed packets to send it back through the mixnet with a request for more SERBs that are then sent back through the mixnet. And then you have enough space, you have enough like space in your envelopes, you have enough like payload space to probably write the response that you want to give back. And then it travels all the way back, right? So there's also a balance here as well to be had between like how many Sphinx packets you send with every message, with every request, right? Because that costs you time and energy, because you have to go through the cryptographic operations of like actually like root encrypting these headers. But if you don't send enough, then you also have this you have an additional like full round trip through the mixnet worth of latency, right? And timeouts are a very present thing when you're using the mixnet and trying to kind of integrate it into existing software, as we'll see a little bit later. Okay, so that was Libp2p, that was the mixnet, and now we'll talk about what putting them together kind of gives us, right? So the transport itself is basically centers around this kind of like abstract like connection object in a way that a lot of the work is trying to like emulate more traditional connections, so that the upstream apps that are actually consuming and using this transport don't really have to think about the mixnet as much as possible, right? There's a couple of quirks of why this isn't completely seamless right now, but there is stuff that we can do for that as well. And the two kind of like key features with regards to anonymity and unlinkability that we've added, right? So you can kind of think of them, usually I talk about like the network level and the app level, but the app level in this case is the behavior part of whatever Libp2p stuff you're running, right? So if the transport is basically how you send bytes between people, then the behavior is what bytes you send and to who. So you can kind of think of it like that. So on the networking level, like I said, we had anonymous replies with SERBs. What this means in the peer-to-peer context is you will have a listener, you will have like, there will be some address, maybe it's a boot node or something like this, that, and that address will have been shared with you either through a broadcast mechanism, like a distributed hash table, or like out of band, right? What it means is that like your dialers, so the person on the left-hand side, we can think of as the dialer, and this guy's the receiver. Like the receiver's address, Nym address, has to be broadcast somehow. So there's a way of routing traffic to them. But, and this is one of the key differences, like usually in a peer-to-peer context, you kind of, as soon as your dialer talks to your listener, then they both have this like symmetric view of who they're actually talking to, right? But as soon as you have anonymous replies in here, then you are kind of creating somewhat of a knowledge asymmetry where the listener gets valid responses and does something with them, but it doesn't build up an idea of like who it's talking to in terms of who is dialing it. And so that happens with anonymous replies. On the Libp2p level itself, we've had to kind of emulate something like this. So usually nodes have a long-lived single identity over time, which is usually just like a public key. And in certain frameworks like noise and stuff like this, this is used for like message authentication. But if you kind of, you know, again, looking at this and looking at like the linkability over time, then even though you might not know the IP address of like the person that's dialing you, if it's a consistent peer ID over time, then you start building up a pattern of information about them, right? And that's somewhat, it doesn't completely negate the point, but it's another vector of like being able to create patterns from data that you observe on the network. So what we have done for this is actually every time you make a connection with a peer, you actually regenerate a new peer ID. So you kind of like, and then when you combine these two things, basically you could have boot nodes, or in the case of Celestia, data availability nodes, right? Full nodes, where they get a request for, hey, can I have these fragments of a block to verify that they're right? And it could be 2 people talking to them 100 times, or 1 person talking to them 200 times. There's no way of actually telling how many people, or like how many different peers, or like that are actually run by the same kind of entity, are actually being talked to. So, and what does the transport do? In very standard way with Libp2p, transport is used for the creation of a swarm, multiplexing and everything is handled like that. And we have also had to have had to add the a Nym specific kind of address format, right? So on a very high level, yeah. Yeah, I thought they were there. Here we go. They're actually here. So, yeah. So like, okay. Yeah, exactly. So why is that actually like practically important as opposed to just being like a kind of an abstract privacy ideal? There's a whole kind of set of attacks that are particular to peer-to-peer systems, right? Where you're actually, the peer-to-peer system itself is kind of like assuming or relying on the fact that you start building up this kind of larger view of the network around you, right? And because all nodes are not created equal in these peer-to-peer things, you know, based on their functionality, maybe we're talking about boot nodes, or in the case of Celestia, we're talking about full nodes that are, should I like briefly outline data availability sampling, just so everyone's on the same page, or like is everyone kind of okay with that, the concept of it? Okay. All right, sick. So yeah, basically like all like knowledge attacks in peer-to-peer systems, right? There might be eclipse attacks, selective disclosure attacks, all of this kind of stuff is based on the idea that for whatever reason, Jaya is a full node. I'm requesting, hey, could I have these like fragments of blocks because I want to verify that these things actually exist, right? And if you're able to build up a pattern, or at least identify who that request is coming from, that's when, as a malicious full node, you might be able to make the decision that like, actually, I'm actually going to give you like an incorrect view of the network. Oh. No. So the swarm is basically just the name for like the abstraction that Libp2p uses, and that's kind of like in your code. That is basically the combination of your like transport, so you know what transport protocols you want to talk, plus the behaviors that you want to talk. And by behavior, you know, you might just be running something that like only wants to speak gossip sub or something like this, or just ping, or you know, you might be running a node that runs like the identify protocol because you're just helping other nodes identify themselves, right? And that's kind of, think of the swarm as just like a, that's the abstraction that kind of handles all of that, right? And is basically the thing that your business logic, so to speak, of your app is kind of piping traffic in and out of. Yeah, I suppose basically, yeah, the kind of the quirks of this, right, is that you are creating, like I've already said, this like asymmetric peer knowledge between people, right, which is somewhat different to how peer-to-peer networking kind of usually works. And there are some pros of this, right? So knowledge attacks, the idea that like, as I get a request, because I can tell who the request is coming from, I can alter the information that I give them. So I could give them an incorrect set, or I could say, okay, well, I know that like there are these certain fragments of a block that do exist, so I'll just give people that, and then they won't be able to tell that actually I lied about having like a full copy of a block. Or if you're thinking about networking, in the case of like a distributed hash table, then you know, Jaya's a malicious boot node, and I could go, oh hey, like who else is in the network? What's going on? And she could give me an incorrect view of the rest of the network, which means that then basically I'm only routing my information through peers that she actually runs. Or all of these kind of like knowledge-based attacks rely on the fact, unless you're just like trying to sow chaos, if you're actually trying to do something directed, and especially kind of like set up the situation for more active-based de-anonymization attacks, you kind of have to like get people to use your infrastructure first, right? So that you can start trying to find patterns in the data that moves through it. And by adding the kind of attribute of unlinkability to the peer-to-peer network using the Nym transport, you protect against this, because the ability to actually identify individuals over time is precluded. However, there's some kind of open questions about what this brings up, right? Because, you know, does it affect the, I suppose, P2P-ness of the system, right? Is the creation of this kind of dialer-listener hierarchy, or people who are willing to kind of broadcast their address to be used for whatever, boot nodes, data availability sampling or something, does that kind of affect the P2P-ness, and how does it so do that? Distributed hash tables then become kind of interesting. Usually people use hash tables for both discovering other peers, finding out who is around them, and also actually being able to then route their traffic to them. We would only really use a distributed hash table for like peer discovery, because the Nym client does its own routing. And you're kind of just adding in this like extra complexity to bidirectional interactions, or maybe even stopping some of them. So these are kind of open quirks and questions that come up, and are, some of them will be probably like mitigatable, but this is the kind of, from this proof of concept of like having an unlinkable peer-to-peer transport that's come up kind of in our work. Yes, and one of the kind of pros of how we've done this, or like one of the pros of Libp2p anyway, is that by doing this, you don't like fragment the network at all, right? So because Libp2p has this concept of circuit relays, it basically means that you can have like a peer that will, you know, maybe it speaks both TCP and Nym, and I as a Nym peer want to speak to the TCP peer. It will kind of like take that packet for me and then forward it on. And the nice thing about this is kind of going back to the dappled sunlight metaphor that was being used before, then what you're actually allowing for is you're not saying, oh, okay, well, like actually to make this work, we need to have the entire network like move wholesale or split in half to kind of exist in this, in the kind of privacy context. You can just slowly start kind of like adding nodes to it, and those kind of, you know, darker patches of shade can get bigger, but it can still interact outside of itself, and interact with, I suppose, like ClearNet nodes maybe is the way to think about it. So yes, on the functional side, on the DevX side, I am DevRel after all. Adding a transport basically means that like most devs don't really have to think about it. You don't have to know about how the mixnet works. And because peer-to-peer traffic is already async, then timing delays, no streaming and stuff kind of is a bit nicer than comparative like stream-based applications. That said, timeouts are still a bit of a problem, right? Because you can't, by adding in all of this additional latency on the networking level, then you are adding a bunch of latency that, even though it might not preclude the technical side of stuff, so like handshakes and all of this, a lot of your upstream software has assumptions about internet connectivity and the speed of light and how that then relates to something like a reputation system. So in the Lighthouse consensus client, then one of the ways that it builds up not just a map of who's around it, but actually then adds a reputation score to those people, right, is based on pings. So it just is like, okay, I'm just pinging all of the peers around me, and based on the return, the latency of the full path that you send a ping and you get a pong, then you can go, okay, cool, well they're more responsive, they're more reactive, they're like set up in a way that's they have good connectivity, right? And as soon as you start like adding in, if you had like a bunch of Lighthouse consensus clients that were using the mixnet, even if they were using like via the circuit relays, were able to kind of talk to other Lighthouse clients, they would seem, from the perspective, from the assumptions of that code, that actually like, oh, well, their reputation must be like, their connectivity must actually be like a bit sketchy, right? Which is not necessarily the case. Now, consensus, especially like Ethereum consensus, is a very tight turnaround on a lot of that. And that's kind of, I suppose, like adding this in on hard mode. We will see, it's to be seen whether this will become an issue with Celestia nodes. And ultimately, like most timeout stuff is just like, is a mitigatable problem. But I wanted to bring this slide up because I suppose to get across the idea that like actually like privacy, even if you kind of whack the privacy layer into something like a transport, which most of the time developers won't have to think about, it's not like a silver bullet. You can't just whack everything through it and nothing else changes kind of upstream of it. And yes, so future dev. So at the moment, this is being done in Rust. We're also going to do it in Go. And I'm trying to look as well into like decreasing the session linkability between these connections, like through the peer, even though you can't retain linkability between different connections because you regenerate the peer ID. I'm also looking into how you would maybe decrease that within a connection session itself. So if anyone thinks about this stuff, go for it. Oh, do we have a question? No? Oh, okay. That's all right. Yes, and then the next step will be making a version of the Kademlia DHT that allows you to peer discovery over the mixnet. So the kind of chat demo code, which is actually still running on my laptop because I decided to be a masochist and do a demo on conference Wi-Fi today, which we can all play with afterwards, or like after I finish talking. Yeah, basically like the next thing would be allowing for peer discovery over the mixnet as well, and like working out how that will work with a distributed hash table like Kademlia. And I'm hoping it will be relatively easy because we're just using it for discovery. Routing is done by the mixnet clients themselves. And then there's some kind of early summer R&D, which we will also hopefully be having a bit of a DevNet for in the coming months, is some work we're doing on what we call the Lewis protocol. And that is basically a set of protocol changes to allow us to build a lot of concurrency assumptions into the clients, into like the actual client itself. All right, so which will remove massively reduce the complexity of the code that you as a developer have to work with if you want to build with our SDK, right? And what this also gives us is we're following on from David Fifield's Turbo Tunnel paper, which is this idea of like having a pluggable transport. So really like pulling apart or like having a set of different potential transports that your client can use for its initial connection to the mixnet, right? Like at the moment, it's just a WebSocket, and WebSockets in some places are both easy to spot and easy to censor, or people don't like you making WebSockets, right? So it's this idea of like kind of abstracting away the actual type of connection you make from the functionality of the client itself. Yeah, so that's the kind of future dev stuff. Now, these are the links. So if people want to try out and join the gossip sub chat that currently has 4 people connected and is working on conference Wi-Fi, which I'm quite happy about because I was up until 2 o'clock in the morning fixing it. You can join there. There's instructions on the README and the repo, and there is a subsection which is called Protocol Berg Workshop Chat, which basically like gives you the command that you have to run to do that. And now, if there are any other questions or anything, then we can do those. Otherwise, whoever wants to like have a go at using the P2P gossip sub over the Mixnet chat can and ask questions. Huh? Oops, sorry. Yeah, I got rid of the QR code, didn't I? That was. There we go. Yeah, and so the key. Yep. Yeah. Yes. So yeah, we have a TypeScript SDK as well, which is maybe like a little less featureful than our Rust SDK. Also, I mostly focus on the Rust SDK, so I'm comfy to work with that. Yeah, you said it, not me. So yeah, I kind of skipped past that one. Yeah, I mean, one of the the protocol changes that we're also talking about are, we're focusing on it for censorship resistance, but like actually having the ability to like choose which transport you're using based on the environment you're using does also open it up for like more environments as well, because some environments, much like browsers, for like a good reason, don't really want your process like randomly opening WebSocket connections outside of the browser window, right? Because it kind of somewhat is a bit of a sketchy security model. But yeah, going back to the Lighthouse stuff, then so there's actually the difference between that and the Celestia data availability sampling is maybe interesting to draw the distinction for here, because with creating like unlinkable data availability sampling, what you're basically doing is you're precluding the ability for a node to go, oh, okay, well, I kind of can roughly identify who you are, so I'm going to give you false information, right? For whatever like economic reason that node might do it, which is like, they didn't properly store and actually have the data available, but they don't want everyone to know that, and because they're whatever saving on money, right, by running a smaller server. Whereas in the case of the Lighthouse client stuff, actually it's a censorship resistant one. So there was a study where basically from running a set of consensus clients, you could like fairly trivially start linking the IP address with the public key of an Ethereum validator, right? And the problem there, or like the problem that opened up, was that then you're basically then able to, because you can tell who is going to be the next block producer, you could then DDoS them. So you could essentially kind of like smush, and you could DDoS them to the extent that like any of their requests outside would time out, which would then preclude them from actually generating the block. So you could actually slowly over time basically like form the validator set that you wanted over time, or you could push out validators that you like didn't like for whatever reason. So that's kind of like a different the different kind of attack there, which is really like based on the linkability of your IP address with your public key, which is kind of a similar, like that's what we were already talking about with like these two core unlinkability attributes on the network level and the Libp2p level. Any more questions? Cool. Also, yeah, going to be around all weekend and also at the Web3 Privacy Now hackathon. So if anyone has other questions that come to them, then just come say hi. Also, is anyone trying out the chat? Has anyone joined? Or no? Is compiling Rust on conference Wi-Fi like too much to ask for everyone? Which is fair dues.